Hello everyone. So we will continue the same chapter, classification of elements, and today we'll discuss ionization enthalpy. Now, first of all, what is ionization enthalpy? So it is basically the amount of energy required to remove an electron. An electron from an isolated gaseous state atom. Amount of energy required to remove an electron from isolated gaseous state atom. So basically isolated, it means it is free from any kind of attraction or repulsion. In gaseous state, it is ready to, it can readily release. Like, so only the energy required to remove just an electron. Okay, so it will give a monovalent positive ion. So this is first ionization enthalpy. So removal of first electron gives first ionization. Now, what are the factors on which it will depend? These are the penetration effect. How close is the electron to the nucleus? Shielding. Whether there are any orbitals in between the nucleus and the electron to be excluded. Then what is the electronic configuration? Whether it is fully filled, half filled, or what kind of uh, electronic configuration of the atom is. So we'll discuss these factors one by one. So first is penetration effect. Now, penetration, as I already explained, proximity of an electron in an orbital to the nucleus. So how close is the electron to the nucleus? Now, it depends on which kind of subshell it is in there in the atom. So for each shell, there are subshells. It can be observed the relative density of electron near the nucleus of an atom. Now, if we look into the radial probability distribution functions, we see the electron density of s orbital is closer than the p, then d, right? So it depends on the shape, and then it depends on the principal quantum number also. So the 3s is farther from the 2s, 4s is more farther from the 3s. So likewise. So if we talk about the penetration power, then 2s has greatest, then 2p, then 3s, then 3p, 4s, 3d. It means the 2s electrons have more impact of nuclear charge on them, right? So it means more the closer to the nucleus, it means the electron requires more energy to release from the atom. Next is shielding effect. Shielding. So how it is, shielding can be defined as the effect in which the inner electron develops a shield for the electrons in the outer shell. So in between electrons, in the inner orbitals, in between orbitals. So how they impact the nuclear charge over the external outermost electron. So the outermost electron experience low effective nuclear charge due to the presence of the in-between orbitals electrons. So they cancel out the nuclear charge. So the actual which is expected is not give its impact on the outermost electron. So we'll talk about the Z effective nuclear charge, which is nuclear charge minus shielding, minus screening constant actually, right? So less the nuclear charge, less the effective nuclear charge, less is the ionization energy required. So ionization energy is directly proportional to the nuclear charge. So greater is the nuclear charge on the electron, so more is the ionization energy is required. So lesser is the penetration, lesser is the nuclear charge, lesser ionization energy is required. So lesser is the nuclear charge, lesser is the effective nuclear charge, so lesser is the ionization. Now, last factor is electronic configuration. So the fully filled and half filled orbitals, they are stable. They are quite stable than the other configurations. Why they are stable? One factor is symmetry, and the other factor is shifting of equal positions for the electrons. So symmetry basically is the reason symmetrical distribution is the reason basically. So if we try to remove electron from the more stable configurations, we need more energy. So as the amount of energy is required more in case half filled and fully filled configurations. So higher ionization enthalpy is required if we have to remove the electron from a half filled orbital or from fully filled orbital. So there are three factors. First is penetration, second is electronic configuration, and the third is shielding. Now, so as we are discussing the trends, so we'll discuss the trends of ionization enthalpy in the periodic table also. So first we will discuss across the period. So left to right, what is happening. So in general, while moving from left to right of the periodic table, the atomic size is decreasing. Atomic size is decreasing. So if we move from left to right, the atomic size is decreasing. Why it is decreasing? Because the effective nuclear charge increasing, because we are filling the electrons in the same principal quantum number. And as an electron is added in the atom, subsequently the proton is also increasing. It means nuclear charge is also increasing as the electron is added in the same principal quantum number. So effective nuclear charge increases as the shielding constant becomes same in this case. So the atom size decreases as we move from left to right. So the force in between the nucleus and the outermost electron increases, due to which the ionization enthalpy in general increases from left to right. So here is a diagram which shows period 2, lithium, helium, boron, carbon, nitrogen, oxygen, fluorine, and neon. So in general, the trend is increase in the ionization enthalpy. However, there are two variations in the trend. One is for beryllium and boron, and the other is nitrogen and oxygen. Boron ionization enthalpy should be more than the beryllium as per the trend. Oxygen should be more as per the trend. Now, what is happening here is, ideally the boron should have more enthalpy, ionization enthalpy than beryllium, but opposite is happening here. The reason behind this is the fully filled subshell of the beryllium. Now, what is the configuration of beryllium is atomic number 4. So it is 1s2 and 2s2. So it means it is fully filled. It is fully filled. 1s2 and 2s2. So the next member is boron, which is 1s2, 2s2, and 1s2, 2s2, and 2p1. Now the penetration of 2s electrons are more than the 2p, the one factor, which is 14, and the other, this is the fully filled configuration. This is the fully filled stable configuration, so it requires higher ionization energy. So that's why the beryllium has exceptionally high. So beryllium should be like here, but it is here actually because of its electronic configuration. So a second, due to the penetration effect, and the first factor is fully filled subshells. So that's why. Now, in case of nitrogen and oxygen, the same thing is happening. So for nitrogen, the configuration is 1s2, 2s2, and 2p3. And 2p3 is the half-filled stable configuration, whereas in comparison to oxygen, it has 2p4. So the removal of electron from the 2p4 is quite easy than the 2p3 configuration. So the same type of you can say anomalies will be observed in third period also. So wherever there is a fully filled configuration or half filled configuration, so those elements have exceptionally higher ionization enthalpy from the normal general trend. So general trend is across the period ionization enthalpy value increases because the atomic size decreases. But there are two exceptions to this generalization. One is the fully filled configuration, and the second is the half filled configuration. So wherever there is a fully filled configuration, the ionization enthalpy is going to be at higher end, and in same for the half filled configurations also. So next we have trend in a group. So what is happening in a group? While moving down the group, the principal quantum number increases. The shell, basically, principal quantum number is increasing. So with the increase in the atomic size, the nuclear charge, effective nuclear charge increases as the electron, the outermost electron goes away from the nucleus. So general trend is its value goes on decreasing as we are moving down the group. So the nuclear charge, effective nuclear charge become less as we move down the group because shells increases as we move down the group. Shells increases, effective nuclear charge will be less. Shielding also increases, which makes the nuclear charge more less, and ultimately the value of ionization enthalpy decreases. So it means it is quite easy to remove electron to make positive ions of the lower members of a group, So more metallic character at the down side of the group. Now next we have successive ionization enthalpies. It means if we remove first electron, it is its first ionization enthalpy. Now if we remove further one more, it is second, then again next one. So third, fourth, fifth. So the amount of enthalpy requires to remove first, second, and subsequent electrons from an gaseous atom is collectively known as successive ionization enthalpies. Now, after the removal of first electron, we get monovalent positive ion. So now the nuclear charge is more as compared to the neutral atom. So it is more difficult to remove further electron. So it is the energy. So if we remove the second electron, so it is second ionization enthalpy. And ionization enthalpy is always measured as per mole, kilojoule per mole. So it is always assessed as for the 1 mole of atoms. And the units used for it is joules or kilojoules. So once you remove the first electron, we're left with a positive ion, monovalent positive ion, and then we will have to remove the electron from a positive ion. It's more difficult, and hence we require more ionization enthalpy as compared from a neutral atom. So here is an example or a question. You can say the fourth ionization enthalpy of aluminium is very large. So we have Al3 positive always. So aluminium is existing as Al3 positive ion. Why it is so? Because its configuration is 1s2, 2s2, 2p6, 3s2, 3p1. So it is easier to remove first three electrons, and after removing first three electrons, its configuration becomes so much stable and with 3 positive charge, so it is very much difficult to remove its fourth electron. So the first 3 electrons removed are the 3 electrons in 3p and 3s, which have less penetration effect, less penetrated. Sorry. So once have gone to the fourth electron, it is to be removed from 2p, so which is much closer to the nucleus and is under the impact of large nuclear charge. So it is difficult to remove the fourth electron. So this is all about the ionization enthalpy. Its trends, it generally increases across the period. But with few exceptions are there. Wherever fully filled configuration of the atom is there or half filled configuration of the atom is there, its value is abnormally high from the trend, which is due to the stability of the atom. And down the group, its value decreases because the size of the atom increases. So bye for now. This is all about the ionization enthalpy.